What if I told you that in just 1 week this September, more asteroids passed closer to Earth than the Moon's orbit than we've ever recorded before? In September 2025, astronomers observed something truly unprecedented. A sudden surge of near-Earth objects began streaking past our planet at distances closer than the Moon's orbit. Among the most notable were asteroids 2025 FA22 and 2025 RJ2, both of which approached much closer than typical for objects of their size. These weren't just small rocks, harmlessly burning up in the atmosphere. FA22, for instance, measured roughly 120 meters across, comparable to the height of a city block, while RJ2 came even closer, passing within a fraction of the lunar distance. This week shattered all previous records for near-Earth encounters. In a single 7-day span, astronomers logged at least 28 separate objects moving past Earth at sublunar distances, tripling the previous weekly high. Observatories worldwide, from Hawaii to Chile and Arizona, worked tirelessly, tracking and cataloging each object as it appeared. Even automated telescopes and newly operational wide-field cameras contributed to this flood of discoveries, picking up objects that might have gone unnoticed just a year ago. The pace was relentless. Each detection triggered a flurry of activity. Astronomers and software systems processed incoming data, flagged new objects, and calculated their orbits within hours. For the first time in decades, the world witnessed just how active and crowded our cosmic neighborhood could become. A vivid reminder that the space around us is far from empty, and that vigilance is the key to planetary safety. While the majority of near-Earth objects detected that week were relatively small, ranging between 8 and 25 meters, their sheer number was enough to capture astronomers' attention. Objects of this size usually pose limited risk because they tend to burn up in the atmosphere, sometimes producing a bright fireball or a harmless meteor shower. However, even small asteroids can create dangerous airbursts, as demonstrated by the Chelyabinsk event in 2013, which injured over 1,000 people and caused widespread property damage. The real concern came from larger objects like 2025 FA22 and 2025 RJ2, measuring up to 120 meters across. These asteroids were massive enough to create city-level devastation if they had entered Earth's atmosphere. A stony asteroid of this size could explode tens of kilometers above the ground, releasing energy equivalent to multiple megatons of TNT. The shockwave would flatten buildings, shatter windows across entire cities, and send flying debris outward, creating chaos for miles around. If composed of iron, the impact could penetrate the atmosphere completely, striking the surface with catastrophic force, forming craters hundreds of meters wide, and triggering fires and long-lasting environmental effects. Even the ocean would not be safe. 2/3 of potential impact sites fall in water, and a strike there could generate massive tsunamis, flooding coastal cities, ports, and islands with little warning. These larger objects highlight a stark reality. While small meteors are mostly harmless, the few larger asteroids are capable of catastrophic destruction, emphasizing why continuous tracking and early warning systems are critical for planetary defense. As the surge of near-Earth objects passed Earth in September 2025, a global network of observatories tracked them in real time. Pan-STARRS in Hawaii, ATLAS in Chile, Rubin Observatory in the Atacama Desert, and Catalina in Arizona scanned the skies nightly, capturing even the faintest moving objects. Automated telescopes and advanced software processed huge streams of data, detecting new asteroids within hours of discovery. This network allowed scientists to quickly calculate trajectories, predict close approaches, and alert planetary defense teams. Even recently, operational observatories like Rubin contributed significant discoveries, thanks to wide-field cameras covering massive sections of the sky. Behind the scenes, human astronomers and automated systems worked together seamlessly, creating Earth's first effective line of defense against potential asteroid threats. the sheer number of near-Earth objects passing closer than the Moon during that single week in September 2025 was staggering. Astronomers estimate that such an event, with more than 25 sublunar objects appearing in 1 week, is a 1 in 2,500-year occurrence. Statistically, the likelihood of witnessing so many close encounters at once is almost negligible, which immediately sparked intense interest and discussion in the scientific community. Experts debated possible explanations. Some suggested that orbital resonances or gravitational nudges could be concentrating these objects along certain paths. Others proposed that a hidden asteroid breakup in the main belt might have suddenly sent a cluster of fragments toward Earth. Many scientists also emphasized the role of advanced detection technology, noting that improvements in wide-field cameras and automated surveys are catching objects that might have gone unnoticed in previous decades. Whatever the cause, the anomaly reminded the world that our cosmic neighborhood is dynamic and sometimes unpredictable. It highlighted how rare and remarkable such a week is, and underscored the importance of continued vigilance, observation, and preparedness in monitoring near-Earth space. The larger asteroids detected, like 2025 FA22 and RJ2, highlight the real risks posed by near-Earth objects. A 120-meter asteroid could produce vastly different effects depending on its composition and where it hits. If it were stony, it might explode high in the atmosphere, generating a powerful airburst with energy equivalent to several megatons of TNT. Such an explosion could flatten buildings, shatter windows for miles, and send flying debris into surrounding neighborhoods. If the asteroid were made of iron, it could survive passage through the atmosphere and strike the ground with devastating force, creating a crater hundreds of meters wide and causing widespread destruction. Ocean impacts would be equally dangerous, sending massive tsunamis radiating outward, flooding coastal cities, ports, and islands with little warning. These scenarios emphasize the vulnerabilities Earth faces from relatively small but fast-moving space objects and the critical need for advanced monitoring and early warning systems. On September 11, 2025, astronomers detected a new comet, SWAN, not through traditional optical telescopes, but via SOHO's SWAN instrument, which measures solar wind and ultraviolet hydrogen emissions. The comet quickly revealed itself as volatile rich, with rapid hydrogen outgassing far exceeding normal levels. Its tail doubled in length overnight, and spectroscopy showed a mix of hydrogen, cyanogen, and carbon compounds streaming from its nucleus. SWAN's behavior was unpredictable. The comet's icy core was fragmenting under solar heating, creating sudden outbursts and jets of material visible to specialized instruments. This made it difficult to forecast its path or activity. For planetary defense teams, SWAN was a clear reminder that threats from space aren't limited to solid asteroids. Some objects, like volatile-rich comets, move and react in ways that challenge traditional monitoring, requiring rapid coordination between satellites, ground-based observatories, and even citizen scientists to track their unpredictable behavior. On April 13, 2029, the asteroid Apophis is set to pass just 32,000 kilometers from Earth, closer than many communication satellites. Once considered a potential impact threat, this flyby now provides a unique opportunity for scientists to observe asteroid behavior up close. The close approach will allow researchers to study how Earth's gravity affects the asteroid, triggering subtle tidal forces that may shift surface rocks, trigger landslides, or even alter the asteroid's overall shape. NASA has dispatched the OSIRIS-APEX spacecraft to rendezvous with Apophis shortly after its flyby, capturing high-resolution images and detailed measurements of any surface changes. The event is a real-world rehearsal for planetary defense, testing our ability to track, model, and respond to close encounters. For scientists, engineers, and the public, Apophis offers a rare chance to witness how small gravitational nudges can influence a wandering asteroid, turning a potential hazard into a valuable experiment in planetary protection. The interstellar comet 3I-ATLAS, officially designated C2025N1, immediately captured the attention of astronomers worldwide due to its highly unusual chemistry. Unlike most comets in our solar system, which release primarily water vapor as they approach the Sun, 3IATLAS outgasses carbon dioxide at an extraordinary rate, roughly 20 times higher than water. This extreme CO2 dominance is unprecedented for a comet of its brightness and activity level, suggesting that 3I-ATLAS formed under very different conditions than the icy bodies we are used to studying. High-resolution spectroscopy revealed yet another puzzling anomaly: a strong atomic nickel signal streaming from the comet's coma, while iron, which normally accompanies nickel in cometary material, was nearly undetectable. In typical solar system comets, nickel and iron are released together as the nucleus heats up and volatile compounds evaporate. The absence of iron in 3I-ATLAS raises questions about its formation history. Some theories suggest that over billions of years drifting through interstellar space, iron-rich compounds may have been stripped away by cosmic radiation or other extreme conditions, leaving behind a nickel-dominated composition. Others speculate that unique chemical processes in its birth system produced this rare elemental pattern, something we have never observed in a comet from our own solar system. The chemical oddities don't end there. Episodic outbursts observed in mid-August revealed that the comet's volatile-rich nucleus is fragmenting under solar heating, exposing fresh layers and releasing sudden bursts of carbon dioxide and other compounds. These outbursts are not only visible as dramatic increases in brightness, but also as changes in the comet's tail structure, with dust streams diverging in multiple directions. The combination of CO2-dominated outgassing, nickel-only emissions, and sudden episodic activity makes 3I-ATLAS a chemical and dynamic anomaly, a true messenger from a colder, more distant corner of the galaxy. This unusual chemistry has profound implications for astronomers. By studying 3I-ATLAS, scientists hope to understand the diversity of comet formation across the galaxy, the long-term effects of interstellar travel on volatile compounds, and how exotic chemical compositions can affect comet behavior as they approach a star. For planetary defense teams and researchers alike, 3I-ATLAS is a reminder that not all objects follow the rules learned from solar system comets, and that each interstellar visitor brings surprises, challenges, and opportunities for discovery. I-ATLAS is not only chemically unusual, but it also displays complex physical behavior that makes predicting its activity challenging. Observations reveal episodic outbursts, where sudden eruptions of gas and dust increase the comet's brightness dramatically in a short time. These outbursts often cause the tail to split into multiple streams, with dust and volatiles moving in different directions, creating a constantly changing appearance. Rotation studies suggest that the nucleus of 3I-ATLAS is slow spinning and may even be tumbling, rotating along a shifting axis. This irregular motion further complicates forecasts as sunlight impacts different areas of the surface unevenly, triggering unpredictable jets and eruptions. With perihelion approaching on October 29, 2025, scientists are racing to track these changes in real time, aiming to understand how this interstellar visitor behaves under the intense heat of the Sun and what its final appearance and activity might be as it passes through the inner solar system. As 3I-ATLAS and the recent wave of near-Earth objects continue to captivate astronomers, a global scientific effort is underway. Researchers from observatories, space agencies, and citizen science networks are working around the clock to track, model, and predict the behavior of these objects in real time. Every new detection, every outburst, and every orbital measurement feeds into complex simulations that help scientists anticipate potential hazards and plan responses. This coordinated effort transforms what could be purely threatening cosmic events into valuable opportunities for study. Planetary defense teams test and refine detection systems, while astrophysicists gain unprecedented insights into interstellar chemistry, comet behavior, and asteroid dynamics. In doing so, humanity not only strengthens its ability to respond to future threats, but also deepens its understanding of the dynamic and sometimes unpredictable nature of our solar system and beyond. As we track 3IATLAS and countless near-Earth objects, one thing becomes clear. Our solar system is alive with motion, surprises, and mysteries waiting to be uncovered. Each asteroid, comet, and interstellar visitor is more than just a potential hazard. It's a messenger, carrying clues about the formation of distant worlds and the dynamic forces that shape our cosmic neighborhood. The efforts of scientists, engineers, and citizen observers around the globe ensure that we are not passive bystanders. With advanced detection technology, real-time monitoring, and international collaboration, humanity is preparing to face these challenges with knowledge, precision, and resilience. Whether it's a sudden outburst from a distant comet, a record-breaking flyby of a near-Earth asteroid, or the unpredictable behavior of an interstellar visitor, the story continues to unfold. By watching, learning, and acting, we not only safeguard our planet, but also deepen our understanding of the universe and our place within it. Stay vigilant, stay curious, and keep looking up. The sky is never as quiet as it seems.